Well, I found myself rather incoherent at the end of the last hour since I hadn't really given the necessary definitions to explain what I wanted to say. The definitions I want are the concepts of manifold in each of the three categories which I talked about. Now, I've already defined the notion of a smooth manifold, and the other definitions are similar. So, for example, we say that, suppose that we have an topological space M. This will be in my third category of topological spaces. M is a topological manifold of dimension M if it satisfies the condition that each X in M has a neighborhood which is isomorphic in the given category to an open set in the standard space, namely the Euclidean space of dimension n. So in this case, the definition comes out if each point X in M has a neighborhood U in M, which is isomorphic, and in this case isomorphism means homeomorphic, to an open set in the standard Euclidean space Rm. And now, if we want to modify this definition so as to apply to the one of the other categories, we just have to change a couple of words. For example, in place of topological, I can put piecewise linear. I'll use the abbreviation PL. In this case, the requirement is that each point in M has a neighborhood U, that is an open neighborhood in M. And in this case, I'll want to put piecewise linearly homeomorphic to an open set in Rm. So the first definition applies if M is a topological space. The second applies if it's a simplicial complex. And you see that the definition of a smooth manifold is completely parallel. It's a subset of Euclidean space such that each point has a neighborhood diffeomorphic to an open set in Rm. And now with this definition, well, I've given this definition, there's a slight generalization which is often very important. That's the concept of a manifold with boundary. And for the concept of a manifold with boundary, everything is the same, except that in taking only Euclidean space as our standard model, we add a new standard model, namely the closed half space HM. This is defined to be a subset of Rm consisting of all points, say x1 up to xm, such that one of the coordinates, say x1, is positive. And if we allow our manifolds, instead of requiring that each point have a neighborhood homeomorphic to an open subset of Rm, if we allow HM also, then we have the concept of a manifold with boundary. So a typical example of a manifold with boundary would be the unit disk. Say DM is a subset of Euclidean space consisting of all points x1 up to xm with, instead of saying the distance from the origin is equal to 1, I say that it's less than or equal to 1. So what I've drawn, for example, is the 2-disk. This is a manifold with boundary, the boundary being the sphere of 1 dimension lower. So this is an example which is appropriate for a smooth manifold with boundary. It's also an example of a topological manifold with boundary. If we want an example of a piecewise linear manifold with boundary, then I'd better take the unit cube, IM, in RM. So in the two-dimensional case, it's the unit square. This is a piecewise linear manifold, and the boundary is the piecewise linear sphere, which we discussed earlier. Well, that was an aside. I know I want to go back to the concept of manifold without boundary. I was trying to describe last time the problem of characterizing the unit sphere. Now, what properties does the unit sphere have in each of our 3 categories? Well, the first property is that it has the homotopy type of the standard sphere. Or rather, well, first property is that it is simply connected and that the homology groups of the sphere will let me, right, hi of x is equal to an infinite cyclic group for I equals 0 into n if we're talking about an n-dimensional sphere, and 0 otherwise. These are properties of the sphere Sn, where n is at least 2. So these are essentially the properties which characterize the homotopy type. The second properties of the sphere are that it is a manifold. It's a manifold in either, that is, a smooth manifold dimension n, or a piecewise linear manifold, or a topological manifold. And perhaps I'd better also add that it's compact. Now, the problem that I want to formulate is, I'll call the Poincare problem. It's just the question of whether these properties which I've listed are sufficient to characterize the sphere among all objects in the given category. So in the smooth case, the question is, if we have a smooth manifold which has the homotopy type of a sphere, does it then follow that it's actually diffeomorphic to a sphere? In the piecewise linear case, the question is, if we have a piecewise linear manifold which has the homotopy type of a sphere, is it then piecewise linearly homeomorphic? In the topological case, if we have a topological manifold which has the homotopy type of a sphere, is it then homeomorphic? This is called the Poincare problem because it's originally due to Poincare in the special case of a 3-dimensional sphere. And roughly speaking, in Poincare's time, it was already clear that this question had an affirmative answer in dimension 2, and if you formulate it correctly, also in dimension 1. And it was expected that the 3-dimensional case would be the next one to be studied, and that if one could work out that, then one might be able to work higher and higher. Well, the situation has worked out rather differently. because it has turned out that the high-dimensional cases are easy, and the three-dimensional case still looks terrible many, many years after Poincaré formulated it. Leave this on and go to the other view graph. Now let me try to describe what we can say about this problem. And I'll first of all look at the topological case. Well, here the answer is that this situation is just what it was in Poincaré's time. The Poincaré problem, or the Poincaré conjecture, let me say, the conjecture that these properties are sufficient to characterize the sphere is true for dimensions, well, 2, since I've excluded 1 in the formulation, and it's unknown for n greater than 2. In the piecewise linear case, the situation is much better. The piecewise linear version of the Poincaré conjecture is true for n equals 2 and for n greater than or equal to 5. And here it's only unknown in the two cases. Unknown for n equals 3 and 4. So the classical case, which Poincaré asked about, still remains unknown. And finally, let's look at the differentiable case. The differentiable version of the Poincaré conjecture turns out to be true if n is equal to 2, 5, 6, or 12. And it turns out to be, it's still, as in the other case, it's unknown for n equals 3 or 4. And it turns out to be false if n is equal to 7, 8, 9, 10, 11, 13, 14, presumably for all larger numbers. Well, it isn't actually known that it's false for all larger numbers. So we see in this case that there's a definite discrepancy between the piecewise linear and the differentiable cases. In the topological case, there simply isn't enough known yet to say exactly what will happen, but one sees here that there are definitely two distinct theories coming in here. And the situation in the differentiable case is not when I say that it's false, I don't mean that it goes completely false, that there are many counterexamples. Actually, the number of counterexamples is quite limited. Suppose we ask how many distinct manifolds are there which have the distinct smooth manifolds of dimension n with the homotopy type of Sn. And actually these are all homeomorphic to Sn. I'm not claiming that this is obvious, it's a deep theorem, but it is true that these manifolds which have the homotopy type of Sn are all homeomorphic to Sn as long as the dimension is large enough. How many manifolds there are? Well, one can give a list of the numbers. And it's a fundamental theorem that these numbers are all finite. There are only finitely many distinct such manifolds. And the numbers will make a little more sense if I don't consider just the smooth manifolds, but put on an extra structure of an orientation. I hope that this concept is more or less clear. Manifold is oriented if we're given, say, I define it, for example, in terms of preferred basis for the tangent space at one point. I won't try to give a precise definition. But each such homotopy sphere will have exactly two orientations, so I'm just picking out one of them in order to make the counting have more sense. And with this notion, we can give a table. So if I'll put the dimension on one side and the number of distinct manifolds on the other side. And distinct means that two manifolds are considered distinct if there's no diffeomorphism from one to the other, which preserves the orientation. Distinct manifolds having a homotopy type of a sphere. And I've said that the problem is unsolved in dimensions 3 and 4, so let's start with dimension 5. Continue, then there's just one manifold in dimension 5. We have a uniqueness theorem, one in dimension 6. Dimension 7, it suddenly jumps up to 28, and jumps down again to 2. And all the numbers look rather erratic. Let's see. Next we have 8, and 6, and 992, and then 1. So when we get up to dimension 12, we have uniqueness again. Notice that 5, 6, and 12 are the dimensions I noted in which one has a unique manifold. And then going on higher, 3, 2, 16,256, 2, 16. And that's as far as the table I have here goes. So that the numbers tend to be larger in dimensions which are congruent to 3 mod 4. This is dimension 15, and the next large number would be in dimension 19. Well, I don't have time now to go into the way in which these numbers are computed, the numbers of distinct differentiable structures on a sphere, if you like. But perhaps I can indicate briefly why it is that the situation comes out so differently in the differentiable category than it does in the piecewise linear category. So I want to try to explain where it is in the course of the analysis of this problem that the differentiable and piecewise linear cases come out to be different. Well, in each case, it's convenient to analyze the problem by comparing it with a slightly different problem, namely the problem of characterizing the n-dimensional disk. So in place of the problem of characterizing the n-sphere, we have the problem of characterizing the n-disk. Or in the piecewise linear case, one should rather call it the n-cube, or n-simplex. Well, the obvious properties of the n-dimensional disk are, first of all, that it has the homotopy type of a point. In other words, it's contractible. And second obvious property is that it's a manifold with boundary. Here we have 3 different categories. You can interpret it as being a manifold with boundary either in the differentiable sense, or the piecewise linear sense, or the topological sense. And there's a third property which turns out to be essential. These two alone are not sufficient. The third property is that the boundary is simply connected. one can give examples of compact manifolds which are contractible, and yet the boundary is not simply connected. Those will not interest us. And finally, the half space, HM, which I described earlier, would satisfy these three properties, and yet still is not, clearly not isomorphic to a disk, so I have to add a fourth condition, namely compactness. So here are the four obvious properties of the n-disk in any one of the four categories, any one of the three categories, the topological, piecewise linear, or smooth categories. And the problem is, do these properties actually characterize the disk? It's an important theorem, which is due in most cases to Smale. I'm stating many theorems together, so there may be a few cases which are handled by different methods, but the essential part is due to Smale, that if n is at least, I'd better be careful and say n at least 6, and if we're in, then these properties characterize the disk in either the differentiable or the piecewise linear cases. Again, the topological case one doesn't know how to handle yet. With these obvious properties that it's contractible, a contractible manifold with boundary, whose boundary is simply connected, is compact. Any differentiable manifold having these properties will be diffeomorphic to the disk. Any piecewise linear manifold with these properties will be piecewise linearly homeomorphic to a cube. This is proved by an extremely complex argument, which I, again, don't have time to go into. But you see, on this level, as long as we're worrying about a disk, it doesn't really matter whether we're dealing in the differentiable or the piecewise linear case. The proofs go along very much in parallel. Either can be proved in parallel, or one can be proved first and the other can be derived from it. And now, once we know this characterization of the n-disk, then we can try to characterize the sphere. And the procedure would go like this. Suppose we're given a manifold M of dimension n. So this should be either a smooth or a piecewise linear, compact n manifold. And we assume that there's no boundary. And we assume that it has the simply connected, and it has the homology of a sphere. And we want to try to show that this manifold is actually isomorphic to the sphere. And the start of an argument would go like this. We take our manifold, and locally it looks just like Euclidean space, since it is a manifold. And in Euclidean space, in any open set in Euclidean space, we can always embed a small disk. So we know that we can embed a disk of dimension n in Mn. Embed, I mean choose a subset of Mn which is piecewise linearly homeomorphic to the disk in the piecewise linear case, or which is diffeomorphic to the disk in the differentiable case. And let me call this embedded disk, suppose we have, say, I as the embedding, so we'll have I of dn embedded as a subset of Mn, where we can take this notation literally in the differentiable case. In the piecewise linear case, one should rather substitute a piecewise linear disk here, a piecewise linear embedding. And now let's look at the complement. So in terms of picture, if this scribble is supposed to represent M, we've embedded a little disk in here, and now what I want to do is bore out the middle of the disk and look at what's left. So we look at Mn with I of the interior of Dn as the points with distance less than 1 from the origin removed. We call this Xn. So in terms of the picture, it's everything except this little area we cut out. And now it's easy to see that this will be a manifold with boundary. And Leah's boundary will have the boundary of the little disk we've removed. And this will, so it'll be a smooth manifold with boundary or a piecewise linear manifold with boundary, depending on which category we're working in. And by using standard algebraic topology, one can compute the homology of this complement, the fundamental group of the complement. One finds it has no homology except in dimension 0. One finds that it's simply connected. And so, using standard homotopy theory, one can prove that this complement is contractible, because it satisfies our first condition. It has the homotopy type of a point. It's certainly a manifold with boundary. Now the boundary, if you notice, is just the standard sphere. So this is isomorphic to the standard sphere by the way it's constructed. So the boundary is certainly simply connected. And we've taken a compact set and removed an open set from it, so what we have is certainly compact. So what we've got, this object Xn, satisfies all 4 conditions. And so if the dimension is at least 6, we can apply Smale's theorem and conclude that if n is greater than or equal to 6, then Xn is either diffeomorphic or piecewise linearly homeomorphic to the standard disk or cube. So now we can describe our manifold in a new way, our manifold M. It's obtained by taking 2 disks, namely this disk which we embedded and Xn. We have 2 disks, that is 2 objects in our category which are isomorphic in the category to disks, and these are disjoint except along the boundaries. The boundaries are matched up. So this says that our given manifold is obtained by 2 disks from 2 copies of the standard disk by matching the boundaries together under some isomorphism in the category. So we can represent it by the following. Let's see, perhaps I better leave that and go over here again. We have the following situation. We have 2 copies of the standard N disk. Let me draw the picture in the differentiable case first. There's supposed to be 2 identical disks. And we have a, that is, let me do things this way. I take 2 copies of the standard disk. I map one isomorphically onto the inside disk. I map the other isomorphically onto the outside. And then we notice that boundary points correspond. That is, we take the diffeomorphism from one of my standard disks to here, and from the other standard disk to here, and corresponding points on the boundary can be, if they're represented back on this picture, will not necessarily correspond in any obvious way. But by this construction, we've defined an isomorphism from the boundary here to the boundary here. So F is a mapping from Sn-1 to Sn-1, and by the construction, it has a 2-sided inverse. So it is in the differentiable case, a diffeomorphism. And in the piecewise linear case, it will be a piecewise linear homeomorphism. And now, if we have this situation, we have 2 disks and a matching together of their boundaries, then we can take these two copies of the disk and try to paste them together using this diffeomorphism. And it turns out that one gets a differentiable manifold in that way, which is essentially well-defined. One has to do a little work, but there are no real problems, and one finds out that this diffeomorphism F completely describes the situation. Now, if we're lucky, if we do things just right, perhaps we can perform the construction so that F is actually the identity map. If we do that, we just had two copies of the standard disk. We patch the boundaries together, or paste the boundaries together in the obvious way, and what we'll get is simply the representation of the standard sphere as the union of two hemispheres. But the trouble is, this doesn't always happen. If you choose just any old diffeomorphism from the Sn-1 to itself, it turns out that what you get is a differentiable manifold, all right, which has the homotopy type of the sphere, but it turns out not always to be diffeomorphic to the sphere. And this is where the argument breaks down, so that in fact we do not get a unique manifold here. But if we carry out this same argument in the piecewise linear case, then we get to this same point, and then we can carry things one step further and show that our manifold actually is isomorphic to the standard sphere. And the reason is that one has the following very elementary lemma, which this lemma now applies to either the piecewise linear or topological cases. It does not apply in the differentiable case. The lemma says the following: any, I'll say, isomorphism that is to be interpreted as piecewise linear homeomorphism or homeomorphism, depending on which case one is considering, from the boundary of the standard cube, I'll write boundary of In to boundary of In. I might as well use In, since that will do as the standard disk in both of these categories, extends to an isomorphism from In to In. And the proof is very easy. We just take the standard cube, In here, and another copy of it here. Now if we have a correspondence F between their boundaries, and we want to extend it over the interior, we extend it as follows. We say that the center point of the cube goes to the center point of this cube, and we require that each line segment joining a boundary point of the cube to the center shall map into a line segment joining the boundary point to the center here. And this defines the mapping uniquely, because each point in the cube lies on exactly one line segment joining the center to the boundary. And we know where the center goes, we know where boundary points go, and the rest of the mapping is uniquely defined. And one just has to stare at this a little bit to check that, in fact, it is true that the mapping defined in this way will always be continuous. And if F happens to be piecewise linear to start with, then the mapping defined in this way will automatically be piecewise linear, because for F to be piecewise linear means that we can chop the boundary up into small simplexes such that on each simplex F is linear. And now if we have any simplex on which F is linear here, joining the simplex up to the center, we get a simplex of one dimension higher on which the extension is also linear. So the proof is almost completely trivial. But notice that this lemma doesn't work in the differentiable category. We can try to perform the same construction. We can take a unit disk, and if we have a mapping of the boundary to itself, we can try to require that each line segment joining the boundary to the center map into a line segment joining the boundary to the center. Again, this defines a perfectly good continuous mapping, and it will be differentiable with one exception, namely that everything goes haywire at the origin. This construction will never give you something which is differentiable at the origin unless you happen to have started out with a rotation. So there's this simple point which illustrates the difference between the differentiable category and the other categories. Now, with the aid of this lemma, if we're in either the piecewise linear or topological categories and we have an object which is formed by taking two n cubes and matching their boundaries under some isomorphism, using this lemma, one sees immediately that the object one has could just as well have been obtained by taking two copies of the n cube and matching their boundaries under the identity. And if one does that, one sees immediately that what one gets is isomorphic to the standard n cube. But in the differentiable case, this turns out to be false. There are some diffeomorphisms of the boundary of a sphere onto itself which simply do not extend to any diffeomorphism of the disk onto itself. It's a little hard to describe one explicitly, but they can be described, or given by rather complicated formulas. They do exist, and if one starts with such a diffeomorphism and performs this construction of pasting the two boundaries together, then one gets a differentiable manifold which is not the same as the standard sphere. Well, I've just described a few properties which help to distinguish between these three categories. It's natural to ask the question as to exactly what relations there are between the categories. If we have an object in one, how can we get to an object in the other? And there are obvious transitions. If we have a piecewise linear manifold, we can simply forget the fact that it's piecewise linear and consider it as a topological manifold. And similarly with a smooth manifold. So in that sense, we get a diagram like this. If we have a smooth manifold, it gives rise to a topological manifold. And similarly, if we have a piecewise linear manifold, it gives rise to a topological manifold. So that we seem to have a situation in which the smooth and piecewise linear theories lie at about the same level. Now, actually, one can go a little sharper. One can make a slightly sharper statement. Namely, one can also give a transition which assigns to each smooth manifold a piecewise linear manifold. And to describe this arrow, I need to discuss the theory of C1 triangulations. The theory of J.H.C. Whitehead. Well, to describe the notion of a C1 triangulation, I first of all have to say what a triangulation is. That's very easy. Suppose that we have here a simplicial complex. It's a topological space which is cut up in a quite explicit way into simplexes. Simplex being simply a convex set in Euclidean space spanned by a finite number of points which are independent in an appropriate sense. So here one has a simplicial complex. I'll think of it as being in some Euclidean space Rk. And over here one has some arbitrary topological space. To match this picture, let me draw it like this. So this is simply a topological space, which we can think of as lying in Euclidean space also, if we like. And now suppose that we have a homeomorphism from one to the other. And such a homeomorphism is called a triangulation of X by definition. H is a triangulation we can ask the triangulation to have special properties. The property I want is the property of being, will only make sense if X is itself as a smooth manifold, or at least that's the only case I want to consider. So now suppose we have this situation. Suppose that we have here a smooth manifold, and to make the picture possible, I'll take it to be a differential, a diffeomorphic to the circle. So here we have M, which is a smooth manifold. And over here, I want to take some simplicial complex. It's cut up explicitly into simplexes. And suppose we have a triangulation of M that is a homeomorphism from the simplicial complex to the smooth manifold. Then I say by definition, H is a smooth triangulation of M. Two conditions are satisfied. First of all, H, as before, to be a triangulation should be a homeomorphism. So H is a homeomorphism from a simplicial complex to a smooth manifold. And the second condition is that if we take any simplex, say delta, and take the restriction of H to delta, this is a mapping from simplex in Euclidean space to a subset of M. The picture subset of M might be some curved segment like this. The requirement is that each of these should be a diffeomorphism. And this should be true for each simplex delta of our simplicial complex. Now, this is using word diffeomorphism in perhaps an unfamiliar context, but if you remember at the beginning of the first lecture, I defined the concept of diffeomorphism for completely arbitrary subsets of Euclidean space, not only for smooth manifolds, and that's important at this point because a simplex certainly is not a smooth manifold, but we can still require that this correspondence, which maps a simplex, perhaps I'd better draw a different picture to, let me draw a two-dimensional picture. Here we have a two-dimensional simplex, and perhaps here a curved two-dimensional surface, and on it a curved simplex. It still makes sense to say that a mapping which carries this rectilinear simplex onto this curved simplex should be a diffeomorphism. According to our definition, it means that both H and its inverse have the property that they can be extended locally to mappings defined on small open sets, which have infinitely many derivatives. Infinitely many continuous derivatives. So, in this way, we have the notion of a C1 triangulation. Or, I'm sorry, what I've defined is the notion of a smooth triangulation. Smooth meaning that we have infinitely many derivatives. Whitehead actually worked originally with mappings having only one continuous derivative, hence the name C1 triangulation. But it doesn't matter. One can do one as well as the other. And Whitehead proved several basic theorems, among them being that one, every smooth manifold M has a smooth triangulation. I'll use this abbreviation for triangulation. And second theorem, even more surprising, is that this smooth triangulation is essentially unique, so that if F mapping one complex K to M and G mapping another complex L to M are both smooth triangulations, then, so in particular, they're both homeomorphisms, and this means that their inverses are well defined, at least as continuous mappings, then the composition applying first F and then G inverse, this will be a mapping from K to L, can be approximated, uniformly approximated, by a piecewise linear homeomorphism. So this tells us that to each smooth manifold we have associated a class of simplicial complexes, namely the ones which appear in such smooth triangulations, and that these are essentially unique, because if we have any two of them, they are piecewise linearly homeomorphic. So in this sense, we can put our three categories in a definite order, or in fact, we can put our four categories in a definite order. Because if we start with a smooth manifold, then using Whitehead's theory of smooth triangulation, we get an essentially unique piecewise linear manifold. And using the piecewise linear manifold and simply forgetting the fact that piecewise linear structure, we get automatically a topological manifold. And finally, we can forget the precise topology, but only remember the homotopy type. So in each case, we have a procedure from going from one thing to the next, and we can ask the question as to whether it's possible to go backwards. Given a homotopy type, does it contain a topological manifold? Given a topological manifold, is it actually homeomorphic to a piecewise linear manifold? Given a piecewise linear manifold, can it be used to C1 triangulate some smooth manifold? And each of these gives us a non-trivial problem that we can study. And I'll try tomorrow to give some account as to what it is possible to say about these various problems. But to give that account, we need a basic tool, which I haven't mentioned yet. The tool is the concept of the tangent bundle. Now, the idea of a tangent bundle is something which is central to the concept of a smooth manifold. And working in these other categories, it's important to generalize this concept of tangent bundle so that it applies also to them. But let me start with the classical notion, the tangent bundle of a smooth manifold. If we stick to the definition which I've given of a smooth manifold as a subset of Euclidean space with a smoothly turning tangent plane, then the definition is quite easy. We start with such a smooth manifold, take any point x on it, then through x there's a unique plane of dimension m, if our manifold has dimension m, which best approximates the manifold. Or if we talk in terms of a local parameterization, so that we have an open set U in the Euclidean space Rm, and a diffeomorphism between U and our in a neighborhood of x in our manifold, then we can describe this in terms of partial derivatives. If we take, so call this h, suppose that we take the partial derivative of h with respect to the ith coordinate. Now here h is to be thought of as a vector function. So this is a vector function of one variable now. And so it's in one variable. Since taking partial derivatives, I'm keeping all coordinates but one fixed, so only moving along a line here. So this line in the open set will correspond to a certain curve in the manifold. And this partial derivative of the vector function with respect to ui is a vector which tells us that, by definition, the tangent vector to this curve. If we have m different coordinate directions, we get m different vectors up here, partial of h with respect to u1, up to partial of h with respect to u m. And these m vectors span a plane they turn out to be the condition that this is a parameter, that this is a manifold, guarantees quite easily that these vectors will be linearly independent. And they span a plane, span an m-dimensional vector space, which is called the tangent space of m at the given point x, and I'll use this notation, tangent space of m at x. And I'll think of this as a subspace of Rk. Well, this has been a definition in terms of the given parameterization, but if you take any other curve going through the given point in the given manifold, one can easily express its tangent vector as a linear combination of these. So one can define it, for example, as the space of all tangent vectors to all possible curves through x in the manifold. And notice that the dimension of this space is equal to the dimension of the manifold. And notice also that if we have any mapping, say from m to n, this should be a smooth mapping. And if we have a point x here and the corresponding point y equals f of x here, then there's a corresponding mapping from the tangent space of m to the tangent space of n. And one could call this mapping the tangent to f at x, or I prefer to call it the derivative of f at x. And in terms of these tangent vectors to curves, one can see this quite simply as follows. Suppose this is m, the point x. Suppose here is n, and the point y. And if we take any curve with the given tangent vector in tangent space of m at x, then this will map under f into some curve over here. That will have the given tangent vector, and the correspondence which assigns to each such vector the corresponding vector over here is called the derivative of the mapping. At the given point. And this, in terms of local coordinates, what the derivative tells you is it's a mapping from an m-dimensional vector space to an n-dimensional vector space, if m and n are the dimensions. So in terms of standard theory of vector spaces, you'd expect such a linear transformation to correspond to an m by n, or to an n by m matrix. In fact, in terms of local coordinates, it is just the matrix of partial derivatives. The partial derivative of the ith coordinate here with respect to the jth coordinate there. And of course, if we take the derivative, if we have a third space, say P, and we have mapping here and here, so y goes into z, then we can consider the composition, G composed with that. And similarly, we can take the derivatives of everything in sight. So we have the tangent space of m at x, tangent space of n at y, the tangent space of p at z, and we have derivative of f, derivative of g, and derivative of g composed with f. And it turns out very easily that this is again a commutative diagram. In other words, if we first take the derivative of f and then the derivative of g, what we get is precisely the derivative of g composed with f. And you see, for example, out of this that suppose we take, as a special case, suppose that f is a diffeomorphism and that g is its inverse. And in that case, we have a diffeomorphism, inverse diffeomorphism, so this composition is the identity. And then one has here a linear mapping, a second linear mapping, and here the identity linear mapping, since it's easy to check that the derivative of the identity map is always the identity linear mapping. So in that case, we have a linear mapping and inverse linear mapping. One can also do things in the opposite order and take first G and then F. Comparing these, we see that for a diffeomorphism, one actually has an isomorphism between vector spaces as derivatives. It's just by looking at these elementary properties, one sees that if F mapping M to N is a diffeomorphism, then the derivative, mapping the tangent space of M at X to the tangent space of N at Y, is an isomorphism of vector spaces. In particular, the two vector spaces must have the same dimension. These are all completely trivial properties. They're nothing much to prove, but we see in that way how easy it is to prove that if two manifolds are diffeomorphic, then they have the same dimension. And one can try to go backwards. In the reverse direction, one has the famous inverse function theorem. It's a statement that, well, in the classical form, if you have a smooth mapping from one open set in Euclidean space to another, and if its matrix of partial derivatives at a point is non-singular, then locally it has an inverse. We can express that the following way. If F mapping M to N is smooth, and if the derivative at X is an isomorphism of vector spaces, then we can say that F maps some neighborhood of X in M diffeomorphically onto an open set in N. This is a classical theorem, but it is one of the basic things one uses over and over again in differential topology. It shows that if we know the derivative of a mapping at a point, we have a strong grasp of the map, at least locally. Well, so far I've described the tangent space at a point, but what I want is the concept of tangent bundle. So if we have a smooth manifold M, then for each point X we have this tangent space, which I'll think of as being a linear space through the origin. And now suppose we consider the set of all pairs, X, V, where X is in M and V is in the tangent space of M at X. So the set of all such pairs is a subset of M cross Rk. For each given X, we have the set of V is a vector space. And this space E is called the tangent manifold of M. It's a manifold of twice the dimension of M, because to each point of M there corresponds a whole M-dimensional vector space. And we have an actual projection map from E to M, carrying xv to x. And this projection map has the property that the inverse image of each point in M is an M-dimensional vector space. So this is what is called an M-dimensional vector bundle. That is, we have a space here, a mapping to a second space. For each point here, the inverse image is a vector space, and this vector space, in a sense which is not hard to make precise, varies continuously with the point. And This is the notion of the tangent bundle, which plays a fundamental role in studying the topology of smooth manifolds and also in studying their differential geometry. So the first thing I'd like to do next time is to try to show how we can get an analogous notion, not only for smooth manifolds, but also for piecewise linear or topological manifolds. Thank you.